Hi, folks. I'm Vanessa Sockett. I'm a principal computer scientist at Lawrence Livermore National Laboratory, and I'm here today to talk about some of our work about hybrid quantum and classical workload management with graph-based scheduling. Let's get started. So many of us as system software developers are asking this question: what might the future look like? And a very likely answer is that the center of the future is hybrid and autonomous, with a specific emphasis on hybrid. We are asking the question, how do I run classical and quantum workloads together? More specifically, how do I co-schedule these workloads? And so one good strategy for going about answering this question is to look at the needs of applications that are going to need these two resource types. So let's start this talk looking at hybrid application designs. Now, the first design is the single evaluation. I want to argue this is the unit that is going to constitute all other designs. In this design, you build a circuit. You then send your circuit to a quantum device. That is going to constitute a task with some number of shots. Then you're going to get a result back. You read the result, you act on it. One simple line of work. More realistically, we have a loop. And so in this variational loop, such as used by QAOA or VQE, we start on classical resources. And maybe this is where we define our circuit, our parameters. We create the circuit, we send it off to the quantum device. The quantum device will take a measurement, send us back perhaps the result of the cost and energy, back to the classical optimizer, but then we're going to tweak our parameters. We're going to keep repeating that loop until we reach some kind of convergence. Or, for example, we reach some kind of metric, like minimizing costs. And so you can imagine in this case, you need multiple calls to a quantum vendor. This is a different design. Now, the third design is embarrassingly parallel or batch. This is the idea that you have independent circuits. You send them all off to devices and they get results back. And you may not care if these aren't perfectly synchronized. Maybe you just care that they all land at the end, and then by the time you do your post-processing, they're all sort of together. And the fan-out design, this is basically where you start with a circuit, you send it to a device, you get back a result, and then you fan it out to many post-process consumers. So when we started working on some of these designs, this is the question that we started with. How does application design influence scheduling? And I'm going to give you a really simple answer for how we were thinking about this. When my application expects a resource to be there, it needs to be there. If it's not there, it may fail. So for example, with MPI, if all of a sudden one of your ranks dies, the entire application is likely to fail. Or if it's resilient to that, you are likely going to have it be waiting for the resource that it needs. Both of these are less than ideal. So now that we understand the applications, let's move into scheduling designs. How do these application needs influence how we design the scheduler? I'm again going to ask the question, how does resource design, so the design of an interface that interacts with a quantum resource, influence scheduling? I want to argue to you that there are two variables that are important to consider here. My ability to schedule, my workload manager's ability to schedule, depends on transparency and control. And so we're going to talk about these both separately, starting with transparency. So let's look at an example. Let's say that we go to a train station to wait for a train. Now there's two extremes that we can have with respect to transparency. Complete transparency would mean that I know that the train is coming at exactly 10:18. I can schedule myself from when I wake up in the morning, brush my teeth, get in my transportation to get to the train station, to be on time so that I am standing at the platform exactly when the train arrives, and I minimize my waiting time on the platform. Now, the other extreme of transparency is I know absolutely nothing. All I know is that the next train is going to depart eventually. I cannot do any intelligent scheduling of myself. I just have to show up to the platform and hope that the train comes. So the lesson here is that when you don't have control, so with the train, we are not controlling the train schedule. You do need a little bit of transparency. So we do know the arrival times of the train, so we can schedule ourselves, even though we don't know the nuanced details of how that's working. So now let's look at control. I think a really good example for control is when you use a cloud provider and you want to create a virtual machine. And so assuming that there's no resource contention, you can typically log in, click a button to create, and then you get your virtual machine. Now, in this case, I have no idea what the cloud vendor is doing on the back end. All I know is that I have control to click a button, get my resource, use the resource, delete it, and I have the control. I know the cost I'm going to be charged. It's exactly what I need. But in most real-world things, we have an intermediate level of control and transparency, such as what we're going to be talking about today with scheduling quantum resources. So let's do some real-world examples for what this might look like. Sending a letter in the mail. When you take that letter, when you write it, you have total control, but the second you drop it in the mailbox, the only choices that you can make are with respect to maybe the speed of delivery, the mechanism, so, UPS, USPS, FedEx, all of these different services. Once you drop it in the box, you lose control. And you just have to have the trust that the mail entity you're giving it to is going to get your letter there in a couple of days or maybe a couple of weeks. The better example is probably with grocery delivery. So when you order your groceries, you might have an app that you log into that says, your order is 8 stops away. And so maybe you're sitting at home in your pajamas and you say, phew, I can still sit around a little longer. I do not need to schedule myself to be presentable because the grocery delivery is far away. However, once it gets closer and it says you are the next stop, you need to know that it's time to change out of your pajamas and be ready. Now, in real world cases with a queue like this, it may not be perfectly in order like that. You may start at position 8, jump down to 2, then back to 6, and then down because others come in that have priority over you. And so there's a little bit of jiggling in that case. So now if we model the scheduling of the grocery delivery as a picture, we start with our order. Then there's some amount of time when I'm waiting in my pajamas, the driver is delivering to other customers. There's the arrival point of the groceries. And if I have scheduled myself correctly, if I have enough information to know when the driver is coming, that means that I will be presentable when the driver has arrived. So the lesson here is that when we don't have complete control or transparency, guaranteed and predictable is a good start. I can generally predict when the driver is coming. I have a pretty good guarantee that my letter is going to get there on time, despite not having total control or transparency. So now let's talk about a problem that we encountered when we were working on some of these designs. We're calling this the 2-queue problem. This is the basic idea that when we submit work to a remote vendor quantum queue, it actually doesn't need to be remote, it's actually just a second queue. We have to coordinate the scheduling of 2 different resources, classical and then the quantum. So this is what we encountered when we were first using Amazon Bracket. These are some of the providers. So superficially, you kind of want to say like, not my queue, not my problem. But then you realize, we kind of need to schedule these resources together. Maybe this is something I need to think about. So let's take a look at that same picture, but now in the context of classical and quantum work. So if we just very naively submit a job that did not think about co-scheduling, what would happen? Well, there would be some amount of time where we're sitting and we're waiting in a vendor quantum queue. Our classical workers, which might be very expensive GPUs, are going to be idle, sitting, waiting. At some point, the quantum will be ready, we'll run our circuit, and then we'll actually use the compute. The problem here, however, and this is the 2-queue problem, is that we have this really long idle time where the nodes are waiting and doing nothing. Maybe that's minutes, maybe it's hours, we do not know. And so ideally, a scheduler that does intelligent co-scheduling can account for that in the sense that it is not going to actually use the classical resources, run that compute until the quantum is ready. And this is exactly what you need for something that's running in a loop. And actually, you need a little bit more. You need to have a guarantee that once you're running, your subsequent requests have priority in the queue, so you're not still waiting again. So now that we've talked about this, we are moving into more details, moving down the layers of abstraction. Let's talk about some quantum workload manager designs. So there's kind of two buckets to think about, and both of these are important. Scheduler integration means that your scheduler has some understanding of quantum as a first-class schedulable resource that takes into account the time things are going to be available with respect to other resources that it knows. Now, execution integration are sort of the niceties, the wrappers that help you handle the environment, the execution, interaction with the quantum resources. You can make a scheduling solution that has one or the other, but arguably the best solution is going to have both. Because if you just do the scheduling integration, you may account for scheduling, but then you don't kind of give a nice wrapper for the user to make the tool really easy to use. So now that we have this holistic picture, we can think about goals for quantum application scheduling and design. We need co-scheduling designs that eliminate or reduce the need for classical resources to wait. We need to solve this 2Q problem, which can be extended to the NQ problem as the world gets more interesting. We also need to securely handle credentials to not give cross-exposure to application state. So if you put, for example, a system-level credential in the system scheduler that goes to all user jobs, that means that a user might be able to peek into the queue and the jobs of other users, which is probably not a good idea. We also need to clearly define the separation between execution and scheduling, as we talked about. We also need them to be flexible for deployment with different institution setups and infrastructure stacks. This is why a lot of the open initiatives that are working on open standards that move across spaces are so important. So now we can kind of put those same two designs into buckets of how we might find different scheduling solutions in the wild. So this is obvious. It could be a co-scheduling solution, just co-scheduling. It could just be a solution that looks at execution. So this could be a workflow tool and application or a workload manager component. And ideally and arguably, the best solutions are in the third bucket. They account for co-scheduling and execution. So I want to now quickly tell you a little bit about Flux Framework because our designs are using Flux Framework components. And probably there are some folks listening right now that have not heard of Flux. So Flux is the workload manager developed at Lawrence Livermore National Laboratory. It combines hierarchical job management with graph-based scheduling. We have a very talented group of developers. The project itself has been around a long time, almost 15 years. We were #1 as the system scheduler on El Capitan in the top 500 list for 2 years in a row, and now we're at #2, which is still very good. Now, what makes Flux special? One of the things is the graph-based scheduler Fluxion. Fluxion, or the Flux Sched project on GitHub, models your cluster resources as a graph. So here is the visual representation of that. There are nodes and edges that represent relationships. So for example, a cluster has children that are racks. The racks have nodes, the nodes have sockets, the sockets have cores. Now, one really awesome thing about working with Fluxion is that it does not care what those nodes and what those edges are. You can model what we see here, which is called the containment subsystem. You could also model network. You could model storage. You could model quantum. You could model an ice cream shop and schedule to it. And that's what makes it so great for research. And so Flux enables converged computing by design because of this flexible graph, but also because it is a framework. A framework means that it is modular. So each of these components that you see here is a different project on GitHub. I can take a specific project and use it for research or development and put it somewhere else. So for example, Flux Sched, this is the project that we are going to use for some of our early prototypes in Kubernetes because Flux Sched can be fit into Kubernetes very easily as a custom scheduler plugin. Now, this is all part of this initiative for converged computing, combining the best of both worlds between cloud and HPC. We've been working on this for quite a few number of years. We initially thought of it as combining like the feature spaces and project. Now we have a more holistic vision where we're thinking of how we're designing the HPC center of the future. And there is a new dimension moving into that, quantum computing, or more generally speaking, this idea that we need to bring custom resources that we haven't thought of 10 years ago into the picture. So this is what we're going to be talking about today with respect to Flux Sched in some of our designs. Let's move into those designs. The first design we decided to implement in Kubernetes because it provided a very easy and quick development environment. This is a project, an update to a project we have called Fluence, a custom Kubernetes scheduler. And again, remember this sort of rule or doctrine that we came up with, that if you don't have complete controller transparency, guaranteed and predictable is a really good start. So a little background on Fluence. It is not a new project. It was first published in 2022 at Canopy HPC at the SC conference. And Fluence is a custom Kubernetes scheduler plugin. You can see the hooks that it uses. And the basic idea is it's going to use Flux Sched to schedule the pods in Kubernetes for your job or for your general abstraction. Now, Fluence at the time solved a lot of problems that were not solved with respect to scalability and scheduling. And let me show you exactly what it did well. So it handled gang scheduling, meaning scheduling a group of pods and making sure that they start together. Because if you use the default scheduler and you don't have pods starting together, in practice, what you get is interleaving of different jobs. And then you'll have one job with maybe just a subset running, and it has to wait for that last worker. So it's a similar problem. You have idle resources. So in these results for 3 different applications, AMG, LAMPS, and QMC pack, what you can see in blue is the default scheduler, where we don't take into account gang scheduling. You see the waiting time really goes up as we increase the ranks. But with Fluence, it stays low because every time we schedule something and we actually create the pod, we know that the entire group can be scheduled. So we wanted to start with Fluence because we wanted to add custom resources to it. And so the first question that we were interested in looking at is how we're going to model these custom resources or quantum devices in the resource graph. We decided to model them at the same level of a rack. So when you make a request, you are scheduling dually classical and quantum resources. Now here is that same plot that we've looked at before, but now with respect to using Fluence. So Fluence is going to use a strategy where it launches a leader job that's going to submit the task to the quantum queue. Fluence is going to deploy what's called a sidecar to that container that's going to monitor the quantum queue and be able to know exactly when the quantum is ready, when your job is number 1 in the queue. Then it's going to send out a request to the scheduler to ungate the pods. So the pods are gated, and then once they're ungated, that will allow them to run. And so what this gives us in practice is all of that idle time is removed, and we start running with good confidence of the classical and the quantum being near each other. Now, here's what that looks like for the user. I mentioned that we need to combine both the execution and the co-scheduling. You add a scheduler named Fluence, and then you say, I would like to have 1 QPU added to that. And then what you might get for your application result is on the right that the pod is submitting to IBM Marrakesh. Here are some of our early experiments with Fluence that show how the gating strategy reduces the worker idle time. So in purple is the default scheduler and green is Fluence. You will notice a couple of things. First, there's huge variability in the waiting time for the default scheduler as we're waiting. There were times running experiments where I was waiting hours for a quantum queue, my job to move to the top. This meant that my classical workers were sitting there running and waiting. You'll also notice there's a lot of outliers, the dots in the plot. So with Fluence, every comparison, Fluence is much faster because we essentially eliminate the idle time. The pods are only ungated when the quantum is ready to run. The other thing that Fluence adds is we have a custom kubectl plugin that will allow you to select based on some parameter of interest. So for example, I want to minimize costs, or maybe I want to execute and I want to minimize the waiting time in the queue. So this runs from the user space where they have access to credentials and they can query the quantum queue and then check for this and then submit their job saying, I would like this particular simulator or quantum device. We also ran experiments for this and we demonstrated that cost and keyword selection does increase the mean cost and the time to the result. And this is sort of an obvious result, but we wanted to run the experiments to actually see it. So once we were moving this design from Kubernetes into Flux Framework and Flux Core, and again, this is work in progress, this is not merged, we thought of this idea of gating in the context of a reservation, but actually we're calling it a hold. And we're calling it a hold because it's basically going to be a reservation that gets held until we send a signal, an RPC, to release it. And I will show you what that looks like. So let's start first with how we add custom resources to the Fluxion graph from Flux Core. We have an RPC that's called add subgraph. So whether you're running a system instance, like I'm the OpenQSE admin and I own the system instance, or I'm a user and I just started my own Flux instance under a batch job that I control, I can call this RPC to add a subgraph of my custom resources. Now, in this example, this is Quantum, but I want to note that this integration is totally agnostic to that. It does not care if your subgraph is Quantum, or as I said earlier, ice cream shop resources. You are giving it a subgraph to add that you can schedule too, and I think that's really powerful. Now, here's what it might look like for Quantum vendors. We decided to model both the vendor, the name, and the particular Quantum device as a type, just to kind of make the query simpler for this first prototype. Some details that aren't really important for the talk, but for now, we are requesting the QPU as exclusive, and we're loading with a particular match format that gives us more metadata back about what we have actually received. So what's the strategy? The strategy is basically to reserve the classical first and then hold until it's ready. So in this design, we're essentially sending out a scout job that's going to do that queue monitoring and then unhold or release the reservation when it determines they're ready. And our sort of three parameters, our three goals are similar to before. We know that we're interacting with external Quantum resources. We do not control them, and we only have a little bit of transparency. We do not want to have idle resources, expensive GPUs running. And we also want it to be simple in the sense that it's one user action. It's not complicated from a usability standpoint. So how are we handling this? Well, Flux has a client plugin interface. So we write a specific Quantum-specific client plugin where we can add specific flags to say, I want to run on IBM, and actually I want to specifically run on IBM Brisbane. Here's my application. So what the client plugin is going to do is it's going to split that work into the classical resources that are needed. They are going to be held as a reservation. It is then going to send out a scout that is going to submit the task to the queue and again do the monitoring until the Quantum is ready. And if you're interested, this is what a piece of the job specifications look like for each of the classical and the scout. The best way to think about this is that if all of the resources of your system instance or your user instance are a graph, each of these job specifications represents a shape with a particular count that you have to search for in the graph. And so when we're doing the graph traversal, if we can find the right count of the shape that's needed, that's a match that will return back the match, and you can schedule the work. So here's what this looks like, again, in this design we've been showing, but now we've modified it for Flux Core. So we have a scout job that serves as this leader that's going to submit the task and watch the queue. The classical worker nodes are held, they are reserved. When the queue is ready, we send an RPC to the scheduler, sched Fluxion queue manager release. That sets hold to false, it releases it, and then the reservation can be allocated. And then you have your compute running. And then the scout job sends the session ID to the compute. How this is done can be done multiple ways, and we haven't decided on anything. It could be as simple as shared on a file system in a directory that the user owns, or we could use some kind of key value store. Now, for vendor-specific logic, right now we're just doing simple flags, and here's 3 examples that I've been testing. Mock is for testing on GitHub. QRMI with IBM backend is for that interface. And then, of course, Amazon Bracket has its own interactions. These are all under development, by the way. Under development, we will definitely be changing this. This is mostly to enable us to run experiments. And I again want to point out the separation of responsibility. FluxSched does not know and does not need to know anything about Quantum. It just has this general design for hold and release with RPCs. It has the add subgraph RPC for some kind of custom resource. It is able to have this idea of a held reservation. It has no vendor or resource specific knowledge, and that's really important because we can apply it to things other than Quantum. Now, the library that adds the Quantum logic is called Flux Quantum. This is where we're basically going to be calling that add subgraph. We add the client plugin. We do have vendor selection in backends, and this is where we define the logic for the scout. Okay, I want to briefly touch on workflow tools because this has been a big topic of discussion in the community. Can we place responsibility for coordination and execution on a workflow tool? Let's take a look. So here is a tool called SnakeMake. It is predominantly used by the biosciences community, a little bit of physics and biophysics too. And what you're looking at is a snake file. A snake file is analogous to a make file where you have an all command that's going to be the final output. And then each rule in the snake file is a scoped step. It can include application or vendor-specific logic or expertise. So for example, in the first rule, this is creating a session for QRMI. Anyone that needs to do this operation doesn't need to write a bunch of Python code and redundantly do it. They can just add this rule to their snake file, and they know that it was written by the experts in the space that has best practices. This allows users to kind of assemble workflows together like Legos. And then, of course, so could this work for quantum? Well, if you just had a workflow that was serial, so step A, B, C, maybe it would work okay. Let's look at that in more detail. So a workflow can orchestrate quantum, but it can't really co-schedule. So here what we're looking at what our workflow tool can do really well. It can run step A, B, C. It can give its rule its own environment, kind of set up things, read in parameters, run things. It will create a DAG, a directed acyclic graph, to make sure that it's done it right. It will, however, be using an executor backend to essentially submit to some workload manager queue. And so it's not actually doing scheduling, it's just doing that submission step. So it's great for orchestration, but orchestration is not the same thing as co-scheduling. The workflow tool, for example, if we brought in our Scout design here, let's say we received notice that the quantum was ready, and then we dispatched our classical. In the best case, we'd get them immediately. Maybe that would work. But in a more likely case, we're still going to be waiting in the classical queue. So again, it's not handling co-scheduling. But here's the good news. The workflow manager and the workload manager can work together as a team to both orchestrate and then execute. So for example, the workflow tool is going to generate the DAG. It's going to run the application. When it submits to the workload manager, it trusts that the workload manager has the expertise to be able to schedule the classical and the quantum resources at the same time, and then deliver back the final result. Doesn't care how that happens, it just wants to be able to get back final the result and then finish with its execution. So these two things need to work together, and they both provide different and useful functionality. Okay, so let's quickly summarize. What I didn't talk about today is the work that we did that led up to this Fluence and Flux Framework work. If you're interested, you can follow this QR code, and you can see the talk on Flux Framework and Quantum early work. I'll talk about QRMI Go and Fluxion Quantum. Now, what we did talk about today is that this work is really exciting, and more specifically, we talked about how application design or the needs are the primary driver of scheduler designs. Now, this isn't a if you build it, they will come. This is a if you build something random that they don't need, they probably won't have any interest at all. Now, the second queue problem, which can be extended to the NQ problem, requires intelligent coordination of queues. We can also model quantum devices as first-class citizens in a resource graph, and this is likely a fluxism. It doesn't have to be that way, but that's how we've decided to do it with Flux. Workflow tools can also collaborate with workload managers to optimally package steps and execute, but they need the help of the workload managers to do that post-scheduling. And so feedback for vendors and some of our future work. For QRMI, there's an acquire call that returns a session ID, but also requires you to submit your application right there. What we think we'd like for co-scheduling is to be able to do that same operation, but not package it with the actual submitted the task, but essentially give a foot in the queue. So then the session ID can be given to the application, which is going to start submitting work when that queue is ready. And so what does this mean after the fact for when we're checking the queue? Well, we can pull for a task ID. That's what we do today, and it works great. But ideally, we get an event-driven notification back so we don't have to do that polling. So our future work, we're going to be doing experiments with Flux Core and both QRMI and Bracket using this new design that I talked about. We are also going to consider other designs. For example, you could imagine instead of having kind of these two jobs, launching one job that starts out really small, the scout waits for the quantum to be ready. When the quantum's ready, the job itself grows. Of course, there's challenging questions to answer in there, like how do you give priority to a job that's going to grow? We can also extend our co-scheduling designs to support local quantum devices, essentially eliminating the 2Q problem because we have total control, total transparency, and the devices that we're modeling are in actually 1Q. I'm predicting this is going to be easier, but we will see. The high-level takeaway from this talk is that quantum awareness can be added to other schedulers with analogous design. They probably won't look exactly like Flux, but as long as you can figure out the right abstractions to handle that co-scheduling, you'll do well. So thank you for listening to this work today. And please reach out to us if you have any questions.